Thanks all for joining. We're going to be reviewing the Atlas Imaging System. It's our newest system by LICORbio. As a quick introduction, my name is Katie Brunetti and I'm the territory manager. We're also joined by Jayce Brandt on the call. He's going to take over the presentation in just a bit, so I'll have him introduce himself at that time. In the meantime, let's hop right into the agenda. So we have a pretty packed agenda. We're going to go through some administrative tasks, touch on an update to the FDA guidance, and then dive into Atlas. Starting with our administrative update. If you've attended any of our previous webinars, you'll know that LICORbio has kind of changed over the years. We were formerly known as LICOR, and LICORbio has spun out of LICOR and has become LICORbio. With that comes a change of website domain, some tax changes, other admin changes, nothing too pressing. The biggest change is that our emails have been updated. So please, if you're trying to contact anyone at LICORbio, make sure you're emailing the @LICORbio instead of @LICOR. Most of this has been changed behind the scenes, but later this month, we will lose access to the @LICORbio. Sorry, later in September, end of September, you will lose access to @LICOR. So please make sure you're emailing us at licorbio.com. As for our last admin update, Jayce and I will be attending the upcoming bio shows and conferences. Actually, since yesterday, this has kind of expanded a bit more. We'll be on campus at Brown at the end of this week. And I think there's one additional conference that we're considering joining later this year. But please look for us. Please come by our booth. We'd be happy to meet in person and kind of talk about a little bit more of what you're doing. All right, so let's transition into our Atlas content. And kind of related to this content is recent changes at the FDA. So in April of this year, the FDA announced a new groundbreaking initiative. The agency is phasing out animal testing requirements and replacing them with more effective human relevant methods. This is beyond animal welfare. This is encouraging the use of AI-based computational models, 3D models like organoids and human organ on a chip systems, as well as real-world safety data from comparable international sources. This really represents a fundamental change in how we evaluate drug safety and efficacy. And what makes this particularly exciting is that these new approach methodologies, or NAMs, can reveal toxicity or adverse events that might otherwise go undetected in animal models. This implementation begins immediately for investigational new drug applications, with companies using modern technologies to receive potentially streamlined FDA review. And because these models more accurately represent what happens in humans, utilizing NAMs can result in faster drug development timelines and reduced R&D costs, all while improving safety through more human relevant testing. I know we have quite a few pharma partners on the line today, and this regulatory shift makes pivoting to 3D and cell-based models not just scientifically advantageous, but strategically essential. And so how does this tie into Atlas? Well, Atlas is LICORbio's newest and most advanced imager. It's designed specifically for 2D and 3D models. It builds on the backbone of our proven technologies, specifically our fluorescence, and it features more lasers than ever, both expanding its capabilities while balancing cost, speed, and insights like no other instrument available. The instrument utilizes a scientific CMOS chip, which is used for high performance imaging and permits high sensitivity, low background, and increased reproducibility. Like all LICORbio instruments, Atlas supports a wide range of assays, and we'll cover as many as we can in this presentation. What truly sets our technology apart is that the input is flexible and the output is standardized. This results in consistent, high-quality data across a plethora of workflows. But don't just take my word for it. Let's dive into the specs. I'm sorry if you can hear the crows. They are crazy out my window right now. All right, so the specifications for the Atlas. The imaging area is 25 centimeters by 18 centimeters. That allows you to image 4 plates or 12 slides with our flexible adapter and a wide range of various culture containers, including petri dishes and microphysiological systems. We are proud to share that dynamic range is greater than 6 logs in a single acquisition. As a refresher, the dynamic range is the amount of light that the imager can capture in a single image. The 6 logs of dynamic range mean it has a 1,000,000-fold range detection capability. This imager will not be saturated with normal biological samples. There's no need to change the exposure time to achieve this or any of the settings to capture this dynamic range. And this is all while maintaining extremely fast scan times, which we'll dive into throughout the presentation. The focal range is -1 millimeters to 5 millimeters, which is super beneficial if your organoids or spheroids are on the larger side. The resolution ranges from 5 to 100 microns, which allows for beautiful pictures of your samples and increased flexibility of your assays. And your data output will include a ZSAC and 2D projections. As for the channel capabilities, there are 4 brightfield channels that allow for the monitoring of morphology, size, shape, and structure of your 3D samples. There's 4 epi-illumination channels and luminescence capabilities, all of which will be discussed throughout the presentation. And finally, the Atlas has 6 lasers, the 375, 488, 520, 640, 685, and 785. Based on our emission and detection filters, this is 21 fluorescent channels that can be used on this instrument, which further increases the flexibility and the number of assays you'll be able to run. And then on a final note, the lasers align nicely with a standard microscope, which will allow you to image samples seamlessly between the Atlas and a scope. So for any of you that are familiar with LICOR, you may be asking what the difference between the Atlas system and the Odyssey systems are. First, let me say that the Atlas has taken over as our most robust system with the highest number of lasers and therefore supporting the most applications. The Odyssey systems, which are our historical systems, excel at one-dimensional assays such as Western blots, gel imaging, slide scanning, and others, as well as 2D assays, including immunocytochemistry, immunofluorescence, cell-based, and plate-based assays. We have been and will continue to set the gold standard of this space with the highest data integrity in our instruments. As for the Atlas has, like I said, been optimized for 2D and 3D imaging application. It excels at imaging plates, organoids, spheroids, and organ on a chip, many of which we have slides for in the presentation. With recent customer demos, we've also seen the Atlas image organoids grown in a dome, fluorescent organoids, and some unique applications that I hope we can share more information soon. And then finally, while some of the specs of the Atlas overlap with the Odyssey series, we have not validated or tested its capabilities for 1D assays. As for other instrumentation in the field, looking at the current landscape of imaging technologies, we see about 3 primary categories, each serving different needs in research. Plate readers excel at high throughput screening, but typically only provide single data points per well with no morphological information. Automated microscopes offer detailed imaging with reconstruction algorithms, but are often slow and resource intensive. And then high contact imagers provide quantitative, in-depth analysis, but can be very expensive, less versatile, and very resource intensive. The Atlas sits uniquely at the intersection of all of these technologies. Unlike plate readers, Atlas captures detailed size and morphology data, as well as absorbency, fluorescence, and luminescence. When compared to traditional automated microscopes, Atlas delivers high throughput performance without sacrificing image quality. Let me be clear, you will not ever hear me or Jayce say that this will replace a microscope. We do not have any magnification on this instrument after all, but there are specific applications that Jayce will review that can be done on Atlas quicker, more efficiently, and with just as high of quality. And finally, Unlike high contact imagers, Atlas offers high-end fluorescent capabilities without the extreme cost and complexity. Again, this isn't a technology that we're saying we can replace, but there are many benefits to using Atlas over HCI to streamline and simplify your workflows. Finally, both automated microscopes and high contact imagers generate extremely large data files and often require extensive training and expertise in both use and data analysis. What makes Atlas truly distinct is the ability to kind of play in all of these spaces. It can perform absorbance, fluorescence, and luminescence, but also capture comprehensive size and morphology data. With Atlas, you're no longer forced to choose between throughput and detail or cost and compatibility. It delivers quantitative morphological analyses while maintaining speed and ease of use. Looping back to that FDA landscape that we talked about earlier, Atlas is well equipped to capture both quantitative metrics of therapy treatments as well as the morphological insights of developing these models. When regulators are asking for more sophisticated human-relevant data from 3D models and organoids, you will have a system that is versatile, easy to use, and provides those digestible data outputs. And for my academic leaders on the call, while drug development might not be your specific focus, the Atlas can be used in many ways that you would use your Odyssey systems. For mechanism of action, drug screening, maintaining the flexibility of assays, all while retaining the highest level of data quality and analysis. Atlas plays in all of these spaces and bridges those gaps seamlessly. All right, so here's some of our pictures. Atlas can really integrate seamlessly throughout the entire 3D modeling. Whether you're working with spheroids, organoids, organ on a chip, or even just cell culture, Atlas supports every critical step of your process. Starting with model development, which is that first column, Atlas can help you determine if your 2D cultures are ready to transition to 3D systems. As I mentioned, Atlas has been optimized to image 2D and 3D systems, so you do have capabilities in both realms. Next, in the growth and treatment phase, you can quickly image after media changes or treatments and critically monitor your size and morphology to determine whether your 3D structures are ready for experimentation. This all comes without the risk of displacement or removal that comes with traditional handling because 3D models can be imaged in their plates or domes. As you can see in that first picture, that's a picture of a plate, a typical plate, not specific to LICOR. Finally, in your assay development phase, Atlas performs fluorescence, luminescence, brightfield, and colorimetric readouts, all in the same fixed platform throughout the entire workflow. And this is, again, all without changing settings or manipulating the instrument. We focus so much on the development and growth of these models, which really is an area that Atlas shines, but we cannot forget that Atlas has numerous fluorescent outputs that provide quantitative analysis for your various workflows. What you're seeing here is a complete 3D workflow solution. Every single image on this slide was acquired on the Atlas and many at beta sites as well. We'll dive deeper into each of these capabilities, but I first wanted to show you the big picture. One instrument supporting your research from model development through final analysis. With that, I'm going to transition over to Jayce to hop into more in-depth analysis of these applications. Oh, Jayce, you're muted.
Yep, I was just saying, let me unmute. Okay, so yes, thank you, Katie. So now we'll dive in a little bit more into sort of how we're developing all these different models and what it looks like to work with this on the Atlas. So we're going to go through some of the stuff that we did both in-house with our R&D, as well as some of the stuff that we worked with our beta sites to develop these models. So the first thing I really want to talk about is setting up sort of the challenges that we've seen working with the more traditional methods. So when using a microscope or something like that, we found that they can be sort of limited in being able to capture the entirety of your sample of your organoid. This is especially true when you're looking at like these large neuronal organoids or like brain organoids. Those can be really big and be really difficult to image with a traditional microscope. So here we see, you know, sort of when you have this automated microscope, this 2x, you get a pretty good picture, you get a full image of this spheroid. But when you start getting into this 4x, so it's 10x, you start losing sort of that bigger picture. You can only see the trees and not the entire forest. And this also comes into play not only with just sort of like your X and Y dimensions, but also your Z. So the more you go up in magnification, the more shallow your depth of focus will be. So you start getting sort of grainier and grainier. You have to take more and more Z-stacks. That increases your file size as well as sort of limiting you to looking at only either, you know, single regions in your organoid for a single image, or you have to sort of stitch them together and you get this vignetting effect. I'll show you that a little bit later on. However, the Atlas is very well positioned. So I just sort of call this more of a macroscope than a microscope. So you're going to get every single sort of detail and image quality you could want within your well. You're getting that full picture, not only in the X and the Y. You know, here you can see that we get the full well. So this is a 96 well, and you can see our paint on spheroid very nicely full, even the smaller BXPC3 spheroid, and you can still zoom in on those optically. So we took this with 5 micron resolution, so you still get some of that finer detail despite being able to see that larger picture. So this is an optical zoom, so you're not getting like true magnification, it's just zooming in, and we have that resolution to determine some of these smaller features. Also, with the Atlas, you don't have to worry about limiting yourself with those smaller, like shallower Z stacks. You'll get the full well up to 1 millimeter with the 1x when you're just looking at it at the 100 micron level. So when you increase resolution, that'll get more shallow, but you're still going to be able to get that entire well. So even if your organoid is, you know, floating in a dome somewhere like a matrigel dome, you're going to be able to capture that image and capture the entire organoid or spheroid. So this is true for 3D systems that I'm showing here, but also true for your 2D system. So here we're looking at some neuronal cells that have been stained with DAPI and nestin. So one thing that I really want to point out here is that the Atlas is really good at imaging entire plates, and it gets that entire well, and it doesn't matter what size of that well is. This is a 6-well plate. So this is a single well from a 6-well plate. You can capture that entire image and be able to get in there and see more of the structure and the sort of not quite subcellular, but like cellular level data for these large neuronal cells. Compare that to something like a microscope. You know, at 10x, you get really fine detail, but you have to either subsample or stitch these together. So you lose that big picture. So I've shown you both sort of like single well and full plate. So you can do both of these on the Atlas, and you can do them sort of simultaneously. And all of this is still going to be able to give you, you know, the resolution of the full plate, and you can zoom in. So you can do this both in it's trans-illumination, which I've been mostly showing, but also you can do this with all of our fluorescent channels. And the really fun part is you can do this so frequently because our scan times are really, really short. So you can do an entire 96 well plate in under a minute. So this allows you the flexibility to image this day to day without, you know, having to worry about taking these long scans, taking these to another place, because this is a benchtop imager. It can sit right beside your incubator, and it's really quick to just move them back and forth. So that's also a lot, you know, nicer, a lot more gentle on your organoids. But we're not just limited to plates, right? So that's only one sort of aspect of the Atlas. We're also very capable in imaging these microphysiological systems. So this works really well with a variety of different chips that we've tried to image on the imager so far. You know, you can get really beautiful full chip pictures of things like the emulate, the Memitos chips, as well as this organic. So this is a really fun image that you'll keep seeing over and over. I just really love the way that these were imaged on there. It sort of looks like a really psychedelic TIE fighter, but you're getting all those like different channels and things with it, and you can optically slice through this chip without actually having to physically slice the chip. That's something that we heard several times from our beta testers or people in the field, that when working with these microphysiological systems, they can be difficult because they have a lot of depth. And some of the current microscopes or things like that, they struggle to get through that because either they're using LEDs or they don't have that sort of depth of focus to really get all of these things all at once in an image. The Atlas excels at that. It has that really deep focal point that you can see all of this in, but also you can do really fine Z-stacks to get optical slices of these chips, and you can stack those up. I'll show that a lot later on. So you can go down to like 0.01 millimeters, and you can get each one of those slices. So you can really stack those up and get full, beautiful images of these microphysiological systems. So that really helps you to develop these systems and make sure that, you know, your proposed platform is going to go as smoothly as possible. And that sort of leads directly into the next phase, which is growing and treating your models, right? So as you're doing this, here's the vignetting that I was talking about. So this can be really important to get this full picture view, this macro view of your organoids, your spheroids, whatever you're growing in your plates, petri dishes, all of these different systems. So in order to get this big picture view where you don't know necessarily where your spheroid or organoid is going to be within a well, you know, both X, Y, but also Z, you have to sort of like find these. It can be a real challenge to do this on microscopes where you have such, you know, narrow, fine fields of view. The way that you combat this is that you have to either choose a single area and just, you know, lose the big picture or lose this track of your sample. This way you're saving time, but you're also sacrificing the full picture because you're subsampling. So you have to hope that you're subsampling in the right place. The alternative is taking many different images and stitching them all together. So this gives this rise to this vignetting effect where you have those differential sort of illuminations at the edge of each image. And when they stitch them together, you can get these sort of square looking things. This also leads to really, really big file sizes. So that can be an issue when you're trying to move images around, or you just, you know, have a computer where you're storing all these. You have to figure out a storage solution in order to keep all these images. And if you're doing this day to day, those can really add up, costing you time, costing you money in those storage spaces. With the Atlas, you don't have to worry about that. Again, you have that entire macro view. You can get it in 52 seconds, and you can image them at varying different resolutions, 5, 10, 100 micron, depending on what you want to do. One of our beta testers really enjoys the Atlas, and I really like their quote that said, you know, once they defined their best imaging setup, taking images was very convenient, and they could scan 12 wells of a 24 plate in less than 5 minutes. And so it's about 8 seconds per well. 12 if you're doing fluorescence. So if you're doing multiple channels in fluorescence, it bumps it up to about 12. But this makes it very easy to incorporate into our daily lab routine. So I really view this as sort of a daily workhorse. You know, this thing is going to be able to churn through your samples and really give you not only big picture, but some nice fine scale detail. Another really fun story is, as we were developing these and growing them, our R&D scientist, she looked at a plate after every single step so that she knew how each step, as she was developing this model, impacted her spheroids. And, you know, she was able to do this because these scans take such a short amount of time that she was able to just do this after every single step. And here you can actually see that she was able to track and find where she lost a spheroid. So this is really great for your record keeping. You know, you can jot this down. You have all these images, so you not only have just like a record of it, but proof for that record. And these file sizes are small enough that you can actually keep them or put them in a report so that you know what you're doing. So that's, you know, again, those 52 seconds per scan. But even if you zoom in, so after you've taken those, you can zoom in on a single well. You can do this in a single workflow, and you can get that morphology over time. So you can look at day one as our cells are sort of this loose amalgamation. They're just starting to form, and then you can see as they form and compact over time. So this was taken at 5 microns. You get really beautiful aggregated cells that then form into this tight, compact spheroid for both our DXPC3 as well as our paint one. organoids. So we were sort of learning how to work with organoids as we were developing this instrument as well. So we were just really impressed with, how fast and how quick we were able to get these. But we're also able to quantify all these within our software. So it's not just taking that image, not just producing a pretty picture. We have the data to back it up. So you don't have to rely on just images, you have numbers. So you can track things like area, your equivalent diameter, your perimeter, and your compactness, all very easily and very intuitively through our upgraded, renewed Image Studio software. I'll touch on that a little bit later as well. So the next step is to build and quantify your assets. Now that you have your model, you know that it's working, you know how to grow it, you're very in touch with your spheroid or organoid, it's time to start building these assays. And so the first one that I've sort of already been talking about is this brightfield assay. So most of these images that I've shown have showcased our capabilities in the brightfield channels. But you may recall that the Atlas has multiple brightfield channels. And that may also lead to the questions like, wait, multiple channels in brightfield? How does that work? What are you talking about here? So brightfield is typically referring to transmitted light through a sample, and most microscopes use a single broadband light source. However, in the Atlas, we use 3 independent light sources, a red, a green, and a blue. And so the Atlas, as well as its predecessor, the ODM, it allows the user to use each light source individually or all 3 at the same time. So we found that single light sources sometimes give better images than using them all at once. For example, the 630 alone tends to give really great spheroid images, and that's mostly what I've been showing you. However, we do recognize that sometimes it's desirable to produce images that are more representative of what our eyes naturally see from papers, presentations, or to just better match results from previous studies using broadband light sources. So in lieu of that, the Atlas gives you the option to build the best assay for your specific model or systems using 1, a pair, or all 3 light sources. So the next part is luminescence. So we've talked a lot about this brightfield already. Let's move on to our luminescence assays. And so here we're looking at sort of the difference between a 2D and a 3D system. So here we have a twofold dilution of PANC1 GFP pancreatic cancer cells, and we're determining viability using a 3D glow ATP HTS viability assay kit. So this is scanned at 100 micron resolution on a whole plate scan and in the luminescent channels. So multiple acquisition times. Here you can see that it's determined, and we can track these over time. So whether you're doing this as a 2D system or a 3D cell culture, you can track these over time, given the luminescence, and it's really easy and really quick on the Atlas Imager. So taking that sort of example, normally you'd probably be doing this on a plate reader or something like that. So what is the benefit of getting an image rather than just getting these numbers? So if you see data that sort of looks like this, would you really know what was happening? So on a plate reader, you would just get these numbers, So if you had something like incomplete lysis, you're losing out on this very tail end of the sensitivity, right? If you were able to see that, oh, I had incomplete lysis, if you had an image and you could physically see that, you'd be able to tell like, oh, there's something wrong here. I think I can do better. Same with bubbles. If you have one with bubbles, you have that sort of overall shift down in your signal. So without having this extra information, this image, it'd be very difficult to determine if there's something you can actually, improve in your process. On the Atlas, you can actually see those things. So right here, you can actually see where you have this incomplete lysis and mixing. So one of the other problems is if you have a plate reader, it's going to give you more noise, more variability when you don't have consistent homogeneous signal over the entire well. And that's because it's just taking a quick subsample, maybe 1 or 2 spots from the well. So if it hits one of these islands of signal, you're getting an errant reading. That's not getting the full thing. With the Atlas, we take the entire well. So you don't have to worry about those islands of signal, and it actually helps later on down, and especially like these fluorescent assays in 2D cell cultures. So with this, we really want to stress that even using more traditional luminescent assays, you get that full picture. So now let's talk about fluorescence. This is, what LICOR is best known for. This is sort of our bread and butter. It's what we are really proud of, and the Atlas just pushes that even further. And it does that by continuing with our, sort of known excellence in the near infrared systems. So you always have your two lasers and filter sets that we're best known for, as well as more of these visible spectrums. So what really sets LICOR apart is not only just having all of these options, but the way that these are built together. So our lasers and our filters are built specifically for each other. They're not broadband sources. They're, a really narrow laser source, and you have a really nice tight filter. So you can get a lot of information. It gives you this ability to multiplex, but you don't have to worry about bleed over from one channel into the next because we're not using those broadband sources. We have very specific filter sets. So you don't have to worry about doing things like doing corrections or things like that if you have to, look at crosstalk or if there's autofluorescence. So here I have something to sort of show my work. So in this image, each one of these, a spheroid is grown in a single well of a 96-well plate and stained only with one dye or left unstain. And then all of these spheroids were imaged with all of the channels enabled to assess the level of crosstalk between them. So after the images were acquired, they were linked, settings are optimized, and the course for each corresponding dye in each channel. So for example, you have your fluorescent 488 in the 488 channel, and the variation for signal in each of these channels is only due to biological differences between the spheroids, such as compactness and dye uptake, as well as the ability of each dye to penetrate the spheroid. You do not have to worry about, something like a more promiscuous stain like host showing up in like your 488A channel. And that's because we have this very specifically built filter set and laser broadband. So even though this is, like I said, sort of a promiscuous dye, and you can have a lot of crosstalk between channels and other systems, that's not an issue on the Atlas. So the multiplexing is really great. It's really powerful. And also you don't have to worry about things like compensation or making sure that, you're limiting out background noise in each one of these channels. That's what allows us to capture really great, multiplexed, multi-channel images like this organics chip. So I also want to show you here that you still have flexibility. Even if you turn all of these on, you still have the ability, much like our previous instruments, to choose which channel you're looking at. So you can, click view or not. And so you can look at each single channel independently. And you can also change the brightness and contrast of each one of those channels individually without ever changing your data. You never have to rescan. You never have to change all of your data. It's still going to be completely quantifiable. And changing that brightness and contrast isn't going to change your numbers that you get. And that's because we have that 6 logs of dynamic range. We're able to capture everything all at once, so you don't have to worry about settings or things like that. We're not measuring pixel intensity. We're looking at the entire range in our software. So, it's always quantifiable, as well as giving you this really beautiful picture with this flexibility. I like to say, it is sort of very flexible input with a more standardized output. And you can do this all on either an entire plate or a single well, and you can do that sort of sequentially. So what you could do here, and what we're showing here, is that you could take a really quick sort of single 100 micron resolution image in the 375 channel, just to find out where your regions of interest are, which wells are actually interesting to you. So then once you've done that, you can then choose to image those wells of interest at a much higher resolution with more channels turned on and everything like that. So you get size and overall signal measured in that big picture, but then you get individual well information where you have multiplex and things like that, all so that you can save time and process these things much quicker. But we also want to note, some very important details. So even though at 100 micron, you get that really nice depth of field, sometimes you want to get to those 5 microns and you want to be able to see each individual slice. How do we make this 2D image 3D? We do that with projections here. So you have the option to change your focal depth from -1 millimeters all the way up to 5 millimeters. And you can do that in incremental adjustments down to 0.01 millimeters. So you can really get fine scale stacking here. This makes it really, really powerful for especially like these chips, or if you have like matrigel domes where you have sort of a bunch of organoids or spheroids stacking up on each other. You can get really crisp, clear pictures that are in this 3D space, and you have options for how you want to project this. You can do min projections, max projections, or medium projections. And you can look at still each single either Z-stack or channel individually in our software. So you don't lose that flexibility, you don't lose that single information as you're building these projections as well. So it's all in a single file, single small file, so you don't have to worry about data management as well. So the next question is, what else can you do? So I've talked a lot about spheroids, organoids, which is definitely one of the main focuses of the Atlas, but that's not all it can do, right? This is still a very versatile instrument. It's still able to do one of my personal favorite assays, which are these immunocytochemistry assays. We call it the in-cell Western, but it's so much more than that. I really think of this as immunocytochemistry on a population level. It's a really fun, flexible assay. This is just a quick general schematic of how you can use this. So you culture your cells in your 96-volt plate. These can be adherent or even non-adherent cells. So, if you have them floating around in your medium, you can still use that. It's very flexible. All you have to do is, grow your cells, stimulate, treat, inhibit, whatever you need to do, whatever your experimental condition is, add that in there, let it sit, let it do its magic, and then you just have to either fix or permeabilize your cells. But this spot is also flexible. So if you have targets that are on the inside of your cell, this is where you would look to permeabilize your cells. If it's on the outside, you don't need to do that. You can do what we call an on-cell Western by just skipping that permeabilization step, or you can do a hybrid of both just by timing that permeabilization correctly. So you can look at both outside targets and inside targets in the same plate, in the same cell line. Then it's going to follow very similar to a Western blot workflow, where you're going to incubate with a blocking buffer, do a couple washes, add in your primary antibody, then your secondary antibody, and then excite this with the lasers. So you're getting all of that specificity of the Western blot with your antibodies, but you're also getting the multiplexing capabilities of the Atlas, and then doing the higher throughput and, let's be honest, sometimes shorter workflow in a plate, because you don't have to worry about that transfer or the gel. All of your signal is right there in the plate. So it's much quicker and easier even than a Western blot. So I want to show my work again. So this assay has been around for a while, and there are some really wonderful publications showing how it can be used out there in the literature. So it's been published thousands of times. It's really great, really well respected. More than happy to send these resources out to anyone who's interested. It's a really powerful, really versatile one. So, you have things where it's comparing it to traditional Westerns and showing how it works in a workflow from this paper. And also all of this is completely quantifiable. So you can do this full 96-well plate and be able to compare it to your normalization factor, track this over time, track this over treatment. Here we're looking at a red dot 1 detected in 700 channel as sort of our normalization, and then looking at a phosphorylation of a specific protein here. So this one is like what it would look like if you were taking it on our original Atlas Imager. However, if you take it on the Atlas, you can now do a single well scan, and you can get a little bit more information on the shape of that data. So while we're not getting subcellular, we can still see sort of the variation within our well and see how much that's impacting, and sort of get an idea of what's going on within our sample. So this is a big topic and something that we're really excited to talk about. And we actually have another webinar coming up for these higher throughput cell-based immunocytochemistry assays. And we'd be really excited if you all joined us for those again. That's going to be September 23rd, 2025 at 10 a.m. So you can just scan this QR code here. And that should take you to a link to sign up. But I'm sure we'll also send some follow-out emails reminding you that this is coming up if you're really interested. So fluorescence isn't where this ends, right? There's still a lot more to this story. So with this trans-illumination in the Atlas Imager, you still have access to some of your more traditional assays that you would normally do on plate readers and things like that. Very easy to port over your ELISAs, Bradfords, BSAs, all on the same instrument. So it just makes it a lot more seamless to move from one assay to the next to sort of really incorporate all your same workflows onto the same instrument. And we have more exciting news because with these more channels, we're also looking to support you to do any sort of like cell health assays. So I sort of sat down and thought about the big 3 cell assays that I used to do when I was developing stuff for biotech. And I thought about how I was always doing like cell proliferation assays, which are really important to measure the number of the cells and the sample, analyze cell viability. I did the super old school and I was just counting them on a hemocytometer. Would have been really lovely to have something like the Atlas to actually do this for me so I could just get a full signal and not have to worry about, subsampling as I'm like scanning through and counting with my clicker. It would be really nice to be able to just take an image of the plate, quantify that signal, and then have it all there. Much more reliable than my eye, I'm sure. I was pretty good, but I don't think I'm as good as the Atlas. The viability, another one that I did a lot. So this one, traditionally, you're looking at enzyme activity, metabolites, here to measure the health and condition of cells overall, and indirectly analyze cell number and cytotoxicity. So some of the more classic ones, MTT, XTT, resizurin, calcium, 3D glow, all of these are going to be available to you on the Atlas. And we'll have kits that are paired that were made specifically for the Atlas, for our laser sets and everything coming out very soon. We're very excited about that. And the final one, and my favorite one, because I did it so much through grad school, is cytotoxicity assays. So I did this all with AOPI on a microscope, and I was individually counting cells in a developing parasitic wasp larvae and watching as they died after they were introduced to a toxin. Really wish I would have had the Atlas because I would have been able to take, these are large structures, right? A single full image and be able to then look at the cell and also the pattern at which my cells were dying. Because one of my big findings was that they died at a very specific pattern. I would have been able to see that so much easier had I had the Atlas to image all of my plates for me with these different dyes that show live and dead cells. So I'm really excited for these, really excited to help people sort of get these started in your labs. So like I said, here's just sort of a couple of the kits that are upcoming. As soon as we have this announcement, I'm sure you'll hear from me. Like I said, I'm really excited about these. And one last final plug, if the Atlas isn't doing enough already for you, it also has the capability to produce some really beautiful slide images. So you can do this either in, your RGB, Hosh thing, sorry, not Hosh there, your typical H&E slides here. So you can see those get a really beautiful macroscopic image of your slides. I really like this for slide triage. So time on the confocal is expensive if you have to rent it out, or it's just, headache inducing, especially if you're going through and looking at blank slides all the time. This is a really quick way to just triage your slides, scan 12 of them all at once, in under or like right around an hour. You can get the full rack of 12 done, and then you only have to take your most important ones to that confocal, and you know that your signal's there. The other really fun thing that I think about when it slides is protein arrays. So the Atlas, I'm going to do that. I'm so used to talking about Odyssey. But the Atlas is, really wonderful for these smaller microarrays because it has that 5 micron resolution. So you can use really small spots either on slides membranes, or even those that are loaded onto plates. So, the Atlas is very, very flexible, and we're really excited to learn what everyone is looking forward to using this for and working with them to sort of make sure that we're covering all those bases that the current solutions are sort of lacking in, so that we can help to make your workflow more reproducible, go faster, and also help you cut down on that time to either find something that is a true hit or weed out those things that aren't. So all that is important. I've showed you a lot of really pretty images, but you got to acquire and analyze your data, right? So wanted to just pop in here to say that Image Studio 6.1 is already out and available for you. And also, it is free. And again, we're going to have another webinar to come for this. If that doesn't come soon enough for you, I'm always willing and always very happy to hop on a personal call with your own data, get into Image Studio, and show you how to analyze these. It's a really quick, intuitive software. If you've used Image Studio in the past for our Odyssey imagers, it's going to feel very similar, and it's got all the things that you love, plus a few additional things with this upgrade. So it's going to be used for both your acquisition and analysis of images. So it's a single piece of software that you're going to use for both of those. It is Mac and PC compatible, still free. And it's also going to be there. So we've tried to unify our LICORbio environment, and it's able to, do both acquisition and analysis on all of both the Odyssey and Atlas family imagers, as well as the Pro. And then I'm just going to put it in there again. It's free. So don't have to worry about adding on all those costs of, different modules or things like that if you have to do stitching and things like that, which you don't need to do. So some of the highlights here are we've added a whole bunch of new channels up here for the Atlas. We've added in some new morphology tools so that you can look at each one of your individual wells and things like that and get those measurements that are really important for the growth of your organoids, spheroids, and things like that. Also, with all of these crazy multiplexing options, we did add a custom color wheel so that you can see, you can choose, and if you're sort of maybe a little neurotic like me and you like to have your figures, like all of your bars, match the colors that are in your images, you can do that now. Also, we added flexibility with this Z stacking and things like that to really specify what your plate looks like. So this makes the Atlas really plate agnostic. As long as it has a clear bottom plate, because we're imaging from the bottom, you're probably going to be able to use that plate. So always happy to work with you on whatever plate you're using to make sure we get all these specs right. Just know that the Atlas is flexible enough and powerful enough to use all of those plates. So now I'm going to turn this over to Katie because I don't talk prices. Oh, Katie, you're muted.
Great. I was confirming everything. Okay, so just to touch on pricing, I know it's an important aspect, but Jayce and I also recognize the funding atmosphere right now is a bit tense. So please let us know what you think of these pricing. And if we want to move forward, we absolutely can. There are two bundle options. The first is the standard and the second is the premium. The difference between the two literally comes down to whether or not you need a preventive maintenance, a yearly preventive maintenance or PM. Included in our bundle is the imager, the computer, 1 year of warranty. All of the acquisition and data analysis software is included. That's a huge cost savings if you think about it. Think about all of the software that you pay for on a yearly basis. Our software is included as a one-time purchase, and it is transferable. If someone leaves your institution, we can transfer the ownership of their license to the next person that comes in. It also includes the accessories, the manual, on-site training and installation, and then ongoing training and support. When you buy a LICORbio instrument, you buy part of Jayce's time, and I say Jayce because he's our scientific expert. You buy his ongoing support. So if you need training come 2 years from now when your grad students have left and you need to train your new students, Jayce can come in and do those retrainings. They do not incur cost. It also comes with new user startup reagents. The price for these two is $188,900, or for the premium option, $205K. But we also recognize that there are limitations to getting these instrumentations, particularly justifying costs like that. So at this point, we are offering free demos. LICORbio will ship an instrument to your site, spend half a day setting it up, and then about 2 to 3 days of on-site instrument use. That is a flexible time frame. If you would like it for longer, for shorter, please let us know. We'll provide guidance on how and what to image, but essentially it's customizable to you and your team. This is an opportunity for you to see image and data that comes off the instrument, and also how easy the instrument is to use and evaluate our technology with relatively low risk. We recognize that demos are extremely important, and now you can do one at your own pace, generate your own preliminary data, and see how this integration works with your existing workflows. Hands-on evaluation also ensures that you can access our instrument's performance and kind of compare it against your specific success criteria, while experiencing firsthand how the technology can accelerate your research timelines. So please take advantage of our free demos. There are no forms to sign or purchases required. I really cannot stress this enough. Just take a look at our tech. It is available. So as a recap on Atlas, this is a quantitative analysis in a single platform across many different imaging options. It is capable of imaging microphysiological systems within one acquisition. There's no stitching required. This uses light scanning with the CMOS detection system and works in the UV, visible, and near infrared space, as well as brightfield and luminescence. It can image a 96-well plate in less than a minute, and it produces smaller file sizes that are more cost efficient, more space efficient, and easier to use. And Image Studio software is a one-time purchase and ensures accurate comparison between data sets. Generally speaking, LICORbio is well regarded within the scientific community. 4 out of 5 customers recommend LICOR, and about 85% of our customers choose to use LICOR again when they upgrade or purchase additional instruments. We are quoted or cited in over 10,000 peer-reviewed publications, so our technology really has been tested within the scientific community. Finally, we really believe in providing an excellent experience. Our support is unmatched through through services that Jayce provides, ongoing training, to the in-house support with our scientists, our research and development team. We will get you answers no matter what your question. Finally, here's our contact information. This is our direct email and phone numbers. Please feel free to email us, call, or text us. You can reach us directly through these phone numbers. Again, we are here to help, so please let us do so. If you have any outstanding questions, let us know. And if you would like a demo or a one-on-one conversation, we can also facilitate that. I don't see any questions in the Q&A. I'll give it a few seconds if anyone wants to post anything in there. And otherwise, thanks so much for joining, everyone, and we hope for some continued conversations moving forward. All right, nothing is in the chat, so thanks everyone. Have a great day.